We're going to continue here with question 11. Systemic hypertension is much more common than pulmonary hypertension. Explain why this is the case based on what you know about the differences between the two major circuits. So what you should consider is how flow, that is the cardiac output overall, is equal to change in pressure divided by the resistance. So that means if my resistance is much lower because the pulmonary trunk is huge, it has a very large diameter, especially compared to the aorta. So now if my resistance is less, then I need less pressure to achieve the same kind of flow. And that gets us actually to question 12. Is cardiac output the flow rate? So the flow, that would be this flow right here, equal in both the pulmonary and the systemic circuits? And that we would have to answer with yes, because the cardiac output is the same whether you're going through the lungs or the body. Your cardiac output overall is 5 liters per minute at rest. And the second half of this question, if resistance in the pulmonary circuit is 5 times less, so 5 times less, that's about right, 5 times less, than the systemic circuit, how would the pressure in these two circuits differ? Well, let's use this example. Let's take a look first at a normal cardiac output. So if we have a flow, cardiac output of 5 liters per minute, how does this come about? Well, we said that the average pressure in the system is approximately equal. So on our 120 over 80 person, the average pressure is about 93 millimeters of the mercury. And I just want to use numbers that are easy to deal with. So let's say our average pressure is 100 millimeters of the mercury. And our resistance in the using these numbers here would have to be what in order to come back with 5? So in other words, 100 divided by what number is going to be 5, the 5 liters per minute? And we would have to say that 100 divided by 20 is going to be 5. So the resistance, this magic number here for our systemic circuit, is 20. Now let's say, now we're told in the pulmonary circuit, so CO, the pulmonary, I'm going to put this, is also equal to 5 liters per minute. So this one here is C, cardiac output systemic. And so the cardiac output for the pulmonary circuit is also 5 liters per minute. But now we're told that the pressure, the resistance is 5 times less. So 20 divided by 5 is equal to 4. So now here, so if we know that the resistance is 4 and we know that we have a cardiac output of 5 liters per minute, then we can calculate that the pressure would have to be 20 in order to make this equation equal. So millimeters of the mercury right here. And you can see that the pressure here is also 5 times less as compared to the systemic circuit. So if the resistance is 5 times less, so we're going from 20 down to 4, then the pressure is also 5 times less, from 100 millimeters of the mercury down to 20 millimeters of the mercury, to achieve the same cardiac output. And so there it is. Here is your explanation of why systemic hypertension is much more common than pulmonary hypertension. That was up here in question 11. That was the first statement right here. Now let's define cardiac cycle here in 13. Well, one cardiac cycle is one full cycle of contraction and relaxation. A lot of times people use an electrocardiogram to define the cardiac cycle, and they would just do a P wave, Q, R, S, and then a T wave, and then we go into the next P wave, Q, R, S, and T. So a typical lead 2 EKG, and then they would say, okay, from R to R, that's one full cardiac cycle. You can take any landmark you wish. You could use the P waves or the T waves, from T to T or from Q to Q, whatever you like, but it's customary to go from R to R to define one full cardiac cycle. Let's move on to experiment B, the heart sound measurements. We're going to skip over a lot of stuff, but a few things are kind of interesting. So from R to R wave, the measurement at rest, it should be about 0.8 seconds. 0.8 seconds. And an exercise, of course, from R to R will be much shorter. Let's see how this would play out. Let's say now from R to R, we're measuring only 0.5 seconds. And then you can calculate the heart rate by calculating 60 seconds, that is per minute, divided by 0.8, and that comes out to be 75 beats per minute, BPMs. Now, if you have 60 divided by 0.5, then of course that would come out to be 120 beats per minute, 120 BPMs. Right there. The length of the from R to S1 is not that relevant. We don't need that. R wave to second sound, we don't really need that either. The duration of the sounds themselves, we don't need. From S1 to S2, none of these measurements are really that relevant. And then, of course, down here, just a few things to say. From R to R, so when you're measuring from these T2 minus T1 measurements, so you're measuring the length from R to R, the duration, that is your heart rate. So that will be giving you a clue about the heart rate. So of course you have to take 60 divided by the measurement, whatever it was in seconds. So divided by the seconds, and you get the heart rate. From R wave to the first sound, that's the time it takes for the depolarization of the ventricle to enough pressure build up to where you have the AV valves closing. From R to the second sound, that would be the time it would take from the depolarization of the ventricles to the closure of the semilunar valves. That means when the pressure is starting to go down again in the ventricles. S1 and S2, well, those are the closures of the AV valves versus the semilunar valves respectively, and the durations really are not that meaningful. And from S1 to S2, the time that it would take between the closure of the AV valves to the semilunar valves, and from S2 to S1, that would be the relaxation phase of the heart, sort of the diastolic portion of your cardiac cycle, and that would be from the closure of the semilunar valves to the closure of the AV valves again. Okay, so let's characterize the relationship between the electrical events and the mechanical events. It's very similar to what we talked about with the skeletal muscle. You should always think of the electrical events, they always have to come first. You have to stimulate the muscle, and then the mechanical events, the actual contraction follows that. So there will be always this little lag time where the calcium has to be released and the troponin, tropomyosin story has to happen, and then the actin and myosin can actually interact, and that's when you get the contraction. So the time it takes between the stimulation, so the electrical events, it's the stimulation, and then the mechanical events, they are characterized by all these molecular events that have to happen inside of the muscle cell itself. So the calcium has to be released. It has to bind to troponin for then to allow the actin and myosin to interact with one another and cause the active cross-bridge cycling. So that's when the pressure is going to go up. So basically, the relationship between electrical events and mechanical events is that these have to come first, and then the mechanical events come second. And that's, we notice as excitation, contraction, coupling. And a lot of it, of course, revolves around that calcium release that then allows ultimately the actin and myosin to interact with one another. Now moving on, so we're going to skip question 16, 17, and 18 because we didn't do that, and you don't have any data, and it's really meaningless to try to make up some data and try to explain this, and it's not important. So you don't miss anything. Which of the 4 heart sounds, so let's do 19, which of the 4 heart sounds, and we said we're going to settle for 2 heart sounds. We're just going to go with S1 and S2, as loud as at rest. Well, the biggest valves are definitely the AV valves. However, they are deeper inside of your muscle, inside of your heart itself. And so when you were using a surface stethoscope, a membrane, to listen to the heart sounds, you'll probably hear the S2, the closure of the semilunar valves, louder, simply because they're closer to the surface. The S1 should be louder, but you're not inside of the heart listening to it, and so most likely what you actually hear loudest at rest is probably the semilunar valves, the S2, just because they're closer to the surface. And now our last question: does ventricular ejection occur during ventricular depolarization or during ventricular repolarization? Refer to your recording for hints and explain your answer. I'm going to refer you back to that Wiggers diagram, and we're going to take a look at this in a sec, but let's think about this. So ventricular ejection, that means peak contraction of the ventricle. Would that occur during ventricular depolarization, meaning the QRS complex is happening on the EKG tracing, or during ventricular repolarization, that will be the T wave? Now, we just talked about that the electrical events always have to come first. So it's unlikely that the ejection, the peak contraction of the muscle itself, would happen during the QRS complex. That's ventricular depolarization. So unlikely, but intuitively most students would answer ventricular depolarization on this question. Now let me show you why that is wrong and why ventricular ejection, peak contraction of the ventricle, why that has to coincide with ventricular repolarization. So let's go back to that diagram real quick. So here we are in this diagram, and let's take a look at the QRS down here. So here's your QRS. That is ventricular depolarization. And what does it coincide with on the mechanical side here of the heart? The pressure buildup. So here's your pressure. The heart hasn't even started to contract because the electrical events have to always come first, remember. Now, ventricular repolarization, that's represented here by the T wave. And so now you take a look at the T wave. While the T wave is happening on the EKG tracing, go up here all the way, and where you're ending is at peak ventricular systole. So here is your max pressure. This is ventricular ejection. And so now here you visually see that the T wave coincides with peak contraction of the ventricles, and so therefore the answer to that last question was that the ventricular ejection occurs during ventricular repolarization. That's the T wave on the EKG recording. Okay, that's it for this lab. We will have a quiz on this next week, so be sure that you go through this. Also, be sure that you take a look at those videos that I posted, especially the diving reflex. Kind of interesting how that works, and also the diving reflex in children is interesting. Most people would not dare throw their infant. It works best actually for babies less than 6 months old, but most people wouldn't just throw their baby, their 3-month-old, in the pool and say ha ha, but actually babies enjoy that, and they will reflexively close the entrance to the trachea, and so therefore they will not get any water into the lungs, and so they're quite happy and totally immersed underwater. So take a look at those videos with the babies underwater, and also with the adults that are trying to get the diving reflex going by putting their head into some cold water. And be sure that you take a look at the terms and be ready for the quiz for next week.